As Iman mentioned, I'm from Berkeley, and you've all probably heard stories about the long-haired, freaky hippies at Berkeley. I'm here to tell you that that's all true. You can see that by this carved Halloween pumpkin here, which even has long hair in Berkeley. So, having bombed that joke, let's move on. And I'm going to talk about switched-capacitor circuits, how they're used in modern times. Switched-capacitor circuits, does anybody know when they were first conceived? Well, just a piece of advice, anytime you're asked this question in the future, say, I think Maxwell thought of that. So if you go back to Maxwell's treatise, which was published 1874, I guess, or this 1873, he talks about a galvanometer swinging back and forth between some condensers and transferring current in the same manner that a switched capacitor circuit does. So the correct answer is Maxwell. If any of you, you're probably too young to have bucket lists, but if you want to have a bucket list, you should put on your bucket list before you die to read Maxwell's treatise. I don't intend to die soon, so I haven't read it yet. Okay? Okay, so in modern times, switched capacitor circuits came about mostly through the work at Berkeley under Paul Gray, Dave Hodges, and Bob Broderson. And this came about because Dave Hodges had been at Bell Labs, and he understood the analog telephone system at that time. And he knew that it needed to be replaced by something that was compatible with digital techniques if you were going to switch to the digital telephone system. And so all of this effort on CMOS analog started then. So some work on capacitor A to D converters, 75. Civitas did some work on op amps, and a couple of other people worked on filters and so on. Those were all the basic components for the telephone system that we all use now. So here's what I'll try to do today. I'll talk about CMOS power amplifiers in particular, and the application of switched capacitor techniques to those. One of the things I'll show you is emphasis on efficiency of power amps. And you'll see that it goes up slowly, maybe 5% a year. Well, the thing to keep in mind is if the efficiency of your cell phones goes up 5%, that's enough energy saved to run the whole Seattle metropolitan area for a year. So it's pretty important and pretty significant if you can improve these efficiencies. So I'll talk about PAs and switched capacitor power amplifier, which is kind of a weird thing, and then some work on compressed sensing for biomedical applications. I was talking to Professor Chen this morning, and I was pleased to learn that he's done some really neat work on compressed sensing for A to D testing as well. Okay, so I'm going to do some professor types things here, show you some basic stuff, and then try to lead that into the switched capacitor PAs. So if we talk about power amplifiers, they're basically two flavors, chocolate and vanilla. The chocolate flavor is the linear power amplifiers, and those are needed for any kind of standard where the amplitude varies. So obviously if you have standard AM radio signals, for example, the amplitude varies. If you have some of the modern quadrature amplitude modulated signals, the amplitude varies and so on. It's important to have linearity over those range of amplitudes. So that's good. They're very linear, but the problem they have is rather bad efficiency. So this is a nice little chart that I like to use to show the different definitions for the different classes. So what this says is that if you have the threshold voltage for the MOSFET, I probably should use this. Whoops, not that. See, that's why I don't use that. If the signal is always above the cutoff, in other words, the amplifier stage is on all the time, that's class A, and class A in the RF world has a maximum efficiency of 50%. If you go to class B, which is here, it's on half the time, off half the time. A lot of distortion, obviously, because you're only amplifying half the signal, but the maximum efficiency here is 78.5%. Very good. Of course, you have too much distortion here, so you try to compromise this and go to somewhere in between, which is class AB here. And another class that hasn't gotten much attention is class C, where you operate the device so that it's hardly ever on. So you think, what's this useful for? Well, it has a great feature. If you look at the maximum efficiency of this thing, it's 100%. What's the drawback? In order to get 100% efficiency, you'd have to have no signal. So that's normally a problem. But if you think weird like I do, you think, okay, where are there applications where you have virtually no signal? And those are applications in power amps that go from sensors on your body, for example, to the cell phone in your pocket, which is kind of the base station for body area networks and body area sensors. So for those applications, if you have little tiny power and high efficiency, that's great. Okay, I'll try this. Good. So the second class, so we did chocolate, now we'll do vanilla. The second class is switching power amplifiers. Those basically for so-called constant envelope signals, or signals that have constant amplitude. If you know radios, you think of frequency modulation as one possibility. You change the frequency, but the amplitude always stays constant. So you don't have to have linearity for that value, for that application. You only have one amplitude, so you don't need linearity. So there are many phase modulated signals that have the same property. So these are great in terms of efficiency. This kind of shows that here you can phase these and set these up in such a way that if you're having a voltage, you have no current. If you have a current, you have no voltage. So you're not dissipating any energy in your switching device, and therefore your efficiency can be 100%. So these are great. This is the classic Class E network, which is one of the switching topologies. So this front end stage here just acts like a switch, and this filters it to give you the desired output signals. I like to point this out because this was published by Sokol and Sokol in what year? 1975, and this was a father-son team. So I published a couple papers with my daughter, and I always use that as an excuse. Okay. Let's move on a level. Let's talk about spectral efficiency versus energy efficiency. So I'm showing three different standards here. Frequency modulated standard here, which has only one amplitude. I'm going to give up on this thing in a minute. Has only one amplitude. This is for a quadrature amplitude modulated standard. And what this shows is the distribution of amplitudes for that particular standard. And as you can see here, the majority of the signals sit at about 60% of full scale. And if we go to 64 quadrature amplitude modulation, which is shown here in this constellation, then most of the signals exist around 25% level or so. So we'll come back to that in a minute. So let's look at the corresponding efficiency curves. Well, if you only have one amplitude, you can use one of the switching topologies like Class E and get this ideally 100% efficiency. Great. If you have something where the amplitude varies like this, you might consider using a Class B stage, for example, and the efficiency looks something like that. What's the problem with this? Well, the peak efficiency, as I said, is great, 78.5%. But if we look at the peak, where most of the signals are here, you see most of the signals are around 50% peak amplitude, which corresponds to an efficiency of about 18% or so. Not very good. Worst case, even worse, an even worse case is if you go to 64 QAM, you see most of the signals are down here around 20% full scale, and the corresponding efficiency is a few percent. So when we started working on PAs, this was sort of a gold mine because efficiency is only 8%. I'm sure we can do better than that, maybe 9 or 10. I mean, we can do better than that. So there was a huge amount of opportunity to improve efficiency for this reason. And as I'll show you, that opportunity still exists to a large extent. Okay, just a word about combining these two. So we know switching amplifier has great efficiency, and we know the linear amplifier has great linearity. So it would be nice to find a compromise between those two that gets the best of both worlds. So there are several different approaches for using these switching PAs in a linear type application. I won't go over these, but feed forward is one approach, feedback is another. The link linear amplifier with nonlinear components, or as I like to call it, the missing link, is another approach. And then a more popular one is this envelope elimination and restoration. So I'll talk a little bit about that. So what this does is it uses a switching PA in the signal path, and it takes the amplitude information and applies that to the power supply. So in effect, you're switching with a variable power supply, so you're switching to get the efficiency and you're varying the power supply to get the linearity or the amplitude information. So that's a very good way to do it. So you have to take the signal, which comes in an IQ form or quadrature form, and convert it into polar form so that you have the amplitude and phase information for those two paths. Now anytime you hear two paths, you should suppress your smirk and wonder, okay, how do you match up these two paths? Because you have an RF path going this way and you have an amplitude path going this way, and somehow they have to arrive at the right time at the output to give you your amplified waveform. So this is the problem with these kinds of approaches. These delay mismatches can really be harmful. Okay, a little bit about these EER techniques. The original one was done by Kahn in 1952. And basically this shows what his idea was. You take an RF signal with amplitude modulation here. You pick off the envelope, which is shown here, and you use that to adjust the supply voltage of your switching amplifier. And through the other path, you just convert the zero crossings here into a square wave and use that square wave to switch the RF class EPA, for example. So very simple architecture. Modern Con looks something like this. You bring in your Cartesian signal and you convert it using a Cordic algorithm, for example, into amplitude and phase information. Use a DAC and a supply modulator to vary the supply of the switching PA, and again you run the switching information into the class EPA, for example. So this is a popular approach. Okay, so we've talked a little bit about the PAs. Now we can say a little bit about the modulators. Remember, what we're trying to do here is we're trying to modulate the power supply voltage of this PA, so we want to know how efficient those modulators are. So this gives you the efficiency characteristics for a simple low dropout regulator. If you look at this thing, it's basically just an op amp and a couple of resistors connected in a simple negative feedback gain configuration. So if you look at the power coming out of this thing, it's obviously I out times V out here. The DC power dissipated across it is obviously VDD times that current. And so you can calculate the efficiency expression here. Even I can do this with my math background. It's just a simple linear relationship. And so what you see in essence is the class E is here if you're at full scale, but anywhere in between you follow this linear characteristic dictated by the LDO in this case. So how much do we gain by doing this? Well, remember we started off here with a few percent efficiency. If we simply do this approach, EER, as I've shown here, you can bring the efficiency up to about 23% or so. Remember, every 5% is running the Seattle area for a year. So going from 5% to 20% is 3 years of heat and electricity and what else do they, well, gardening in Seattle. Okay. So this leads to other ideas. If one variable power supply is good, two must be better, right? So that leads to the idea of a class G power amplifier. And basically that's the same kind of architecture I showed you previously, except now you have two supplies. VDD for handling the largest signals and a VDD over 2, let's say, for handling the smaller signals. So you can set that up quite easily. And in reality, it looks very similar to what we had before, except that the output waveform, small signals are processed by one of these modulators, and the large, shown here in green, are processed by the other. What does this buy you? Well, this is a what do you call a camel with two humps? Is that a dromedary? I can't remember. Anyway, it's got two humps. So what you see here is because of the first supply, we get maximum efficiency at half full scale. And then we turn on the second supply for the larger signals, and we get maximum efficiency at full scale. So again, if we go back to our QAM statistics, which are shown here, here's the probability distribution function. Here's where we were for class B, And here's where we are for class G. So we've raised that up to about 50%, theoretically at least, by not too much sophistication. Are there any questions so far? Sorry I didn't bring any jokes, but I did have a giant hamburger at lunch. That was good. Okay. All right, so that was the theoretical stuff, and here's kind of what some measured results look like. This is the measured characteristic. Remember before it went all the way up to full scale, 100% efficiency, dropped down, went all the way back up again. Here it doesn't quite do that because of various losses and so on. So the efficiency is measured here, the output power is measured here versus signal size. This is the chip, and this is the implementation of it. Key thing here is probably theoretical average efficiency was 24% and measured was 22. So it turned out to be pretty good for what we were doing. Okay. So of course, if analog modulation is good, digital modulation must be better. So what this shows is a digital, so-called digital PA. The idea here is instead of switching an analog supply regulator, not switching, changing it from over some range of levels, what you can do here is to achieve the same thing digitally. And so this is a good example of this. Instead of having one PA, you might have a whole bunch of little baby PAs. And you look at the size of the signal, and instead of changing the supply voltage over here, you change the number of PAs that you're using here. So if it's small, for example, you might only use one of these little bitty baby PAs, and if it's full scale, you might use all n of them. So it's kind of applying digital ideas to this analog power amplifier problem. So of course, this is advantageous. No supply modulator, higher efficiency, smaller area, blah, blah, blah. So what we thought about is if you can do this using current switching, we should be able to do the same thing using capacitor switching. So this led to the idea of switch-capacitor-based power amplifiers. So first, a little basics on switch capacitors, and hold your attacks until later. Here's a couple of ways to look at simple switch capacitor circuits. The upper line of figures here correspond to a pre-charge and reset scheme. So what this shows is we charge a capacitor up to VDD on the left, and then we turn on a switch and share that charge with a clone. So the voltage goes down by 2, and you have twice as much capacitance when you connect them together. So if you do some energy calculations here, you lose half of the energy in this process, and it has to do with losses in the switches as you go between the two capacitors, or loss in the switch. On the other hand, if you do it this way, if you apply a change in voltage to the bottom plate here and have the two capacitors in series, you don't have any switch up here, and you don't lose any energy, obviously, through that path. So we thought, okay, this looks promising for preserving energy efficiency, and it also has an important feature for power amplifier radio applications, which I'll explain in a minute. Okay, so you've seen all these power amplifiers before. Here it is. This is an incredibly simple device. This is a power amplifier. And what's nice about it? There's no amplifier. So, you know, if you have trouble with making amplifiers, don't make amplifiers. That's sort of a design principle. So the way this works is, depending on the amplitude of your signal, you switch one or more of these capacitors between VDD and ground, just like we switched in current sources in and out before. Here we do it with capacitors. So what that does, in effect, is create a square wave on the top plate here that's, whose amplitude is dependent on the code, whose amplitude is dependent on the number of capacitors that you're switching. Capacitors are known to be very linear, so this is a huge advantage that this approach has over the previous approaches that I talked about. So what's the rest of this? Well, this is capacitors providing the amplitude information. This is an L and for frequency tuning, and this is your load resistance out here. if you're going to tune your radio to a frequency, what do you need to do? You need to specify, remember, omega naught equals 1 over square root of L times C. I see some students tending to remember that. Same thing here. This tuning network selects the channel, essentially, that you're going to transmit the power over. Notice that a nice feature about this, in addition to not having any switches in the top, is that you have a constant capacitance on the top, irrespective of the switching on the bottom that's connected to this inductor. So it stays tuned to the right frequency no matter what you do. Okay, some blurbs about output power here. I won't spend much time on those. Output power, as you can see here, scales with the number of the total, percentage of the total capacitors that you're switching, power supply voltage, and your reflected impedance here. Okay, where do we lose power? Well, anytime you switch a capacitor, just like in digital circuits, you have dynamic power losses. Dynamic power losses are CV squared F. So when we switch the bottom plate, when we switch the bottom plate of this capacitor, we have dynamic power losses there. Then you can go through the analysis and it looks something like this as a function of code. Okay, so we're almost wrapped up with this part. So there's some stuff here on the efficiency that you see with this approach. And any practical implementations, you have losses in the inductor. They're not ideal. You have switch parasitics, capacitances and resistance and so on, which cause losses. And then you have these other loss mechanisms here associated with the switching, clock distribution, and so on. The nice thing about this is that most of these 5, in fact 3 of these 5, scale down with technology. So as technology continues to scale down, you can expect better and better performance out of this kind of power amplifier. So again, that's an amazing structure. There it is, a power amplifier with no amplifier in it. You've got the tuning network up here, the switch capacitors here, switches here, buffers to drive the switches here, and information to convert the binary code to thermometer code and deal with the amplitude information and so on. So it's a pretty simple structure. PA measurements, this is kind of an interesting dye photo because all of the switch capacitor PA stuff is over here. This is the output matching network with a couple of inductors. So you can kind of see one of the things if you want to improve RF in the future is figure out a way to minimize or totally eliminate the use of inductors. Anyway, here's the output power. Goes up to about, what is that, 25 dBm or something like that, which is 1/4 of a watt. And efficiency is here. So it's peak efficiency is only 45% or so, but down where most of the signals are, the efficiency is pretty good. Okay. And here's some more measurement results that I won't go through. The reason I don't go through this is because you see we don't meet the specs down here. Why is that? Remember I said in the beginning you have to match those 2 paths, and if you don't, you have problems. We didn't match the 2 paths, and so you get this fuzz that pops up. But we've since figured out how to deal with that. Okay? So this is where we all brag about our stuff. Comparing it to previous graduate students and other mere mortals. Key thing to get out of this is average efficiency, which, as you can see, has been coming up and up and up. And power delivered out of this thing, where is that? 25 dBm. So again, about 1/4 of a watt coming out of this. 1/4 of a watt doesn't sound much because most cell phones now require 1 watt of output. But if you look forward to the future, people are talking about massive MIMO arrays with thousands of antennas or thousands of radios on some sort of surface. And if you have all of those antennas, you can focus the signal so precisely that you don't have to have a lot of power in each one of those amplifiers. So the fact that these are very linear and very efficient means that they're going to be used in those kind of applications which are coming, which is pretty important. Okay, a little bit more. This is a Class G switch capacitor PA. I showed you one of these before. What's different here is we can do a lot of switching. So instead of having this bump in efficiency as we switch from the lower regime to the upper regime, you can modify the switching scheme to keep this pretty constant as you go across. So that was a major difference between this design and the previous one. And this is the switching diagram to do that. There's an error in it. Anybody see it? Just kidding. But it just shows generally the modified schemes. Okay. And this is what it looks like. Again, a very, very simple structure. Measured output performance here. You can see efficiency. And this is the switching losses, which are improved by this approach, and the output power. That's what the chip looks like in the measured results. This was done on an Intel process, which is what's the term for that? Ball grid array. Ball grid array, thank you. BGA. So you can see the core of the ECpE there, and the ball grid array, and the inductor and so on were done on the chip that the ball grid array was attached to, or the substrate that the ball grid array was attached to. So peak efficiency here was 45%, very good linearity. In fact, this linearity is a big, big plus for doing advanced signal processing. Okay, performance here, again, we upped the efficiency and so on to now 33%. Now, my wife always asks me, when are you going to retire, Dave? And I always say, I don't know. I don't want to retire. I'm having too much fun. But I finally figured out how to give a quantitative answer to that. If you look at this, we're gaining about 5% efficiency per year. And now we're at 35%. And that means I've got to keep grinding away for at least 13 more years. Okay. All right, so that was an application, a modern application of switch capacitor techniques in RF, multi-gigahertz applications. I want to switch to another extreme now and talk about switch capacitor applications at very low frequencies, like heartbeat frequencies and so on. So we're talking about a few hundred hertz here, or a couple kilohertz at most. So that's what we're going to talk about here, and I'm going to talk about using compressed sensing, which is DeGong's favorite topic lately, in this kind of application. So here's what we had in mind when we started this project. If you look at the way this might work in the real world, you've got patients with all of these sensors on their bodies. I like to say that somebody needs to design a donut sensor. So every time I eat a donut, which I'm not supposed to have, it sends a signal to my wife, and she can complain to me when I get home. So you have all of these sensors, and they will transmit with very little power, because they only have to go a couple feet from wherever the sensor is to the base station cell phone in your pocket, for example. And once it gets there, it can be transmitted to the hospital, and he can charge $500 an hour to look at this and say, you're still alive. So if you look at this system, this all sounds good, but power efficiency is really important with anything on the body. You don't want the doctor to rip you open every 6 months to put in a new battery. So power efficiency is critical. Now, if you look at this system, like an RF system, what consumes most of the power is the so-called power amplifier. Even for this thing, it's called a power amplifier because it's sending an RF signal a couple feet to your cell phone. So if you can do anything to reduce the amount of time that the power amplifier is on, listen more than you talk, you'll save energy. So what we decided here was the best way to do this is to compress the data so that the power amplifier doesn't have to be on as long. So if you look at ECG signals, for example, which I'll show in a minute, you can compress those by a factor of 6 quite accurately. And that means you save 6x in power in terms of how much time your power amplifier is on. So that's all well and good. Of course, there should be some feedback in this, and maybe you change the compression factor depending on whether the doctor is looking for some details or not. So there's some kind of feedback here as well. Okay, compressed sensing system. The approach we took is an analog front end. So here's your sensor. It comes out at maybe a few microvolts level. And you need a low noise amplifier to amplify that up to where it can feed an A to D or some other analog circuitry with high accuracy. So then you have your compressed sensing block here, which takes this time signal X and creates a compressed version Y. That is converted to digital. Then you have digital modulation into the PA, and it's broadcast down to your cell phone in your pocket. So that's the basic architecture, okay? Very simple. So how does compressed sensing work? So I'll show you a little, this is a 12-ball puzzle. What you have here is an experiment where you have 12 balls, 11 white ones and 1 black one. So the white ones each weigh 1 gram in this case, and the black one weighs 100 grams. So your job is to figure out which ball is the heavy ball. Now, if I was at Berkeley, I would describe the Stanford approach to this problem, which would be to take 12 scales, put 1 ball on each scale, and the one that said 100 grams, I'd say, aha, that's the heavy one. But there are more clever ways to do that. One way you could think is I'll do a binary search. I'll look at half at a time, and then I'll look at whichever has the heaviest. I'll break that by a factor of 2, and so on. You could get there reasonably efficiently that way. But there are ways to do even better. And let me give you an example of that. So let me give you some intuition for compressed sensing. And this is surprisingly simple mathematically. So what I show here is the 12 balls, and these are the possible outcomes of those 12 measurements. So scale 1 would say 1 gram if we selected that. Scale 10 would say 100 grams if we selected that, and so on. How do we select them? We use this so-called measurement matrix. So in this case, it's just, we're going to measure these one at a time, one after the other, until we go through all 12. Just the identity matrix. And this is, so these are the inputs, that's the identity matrix, and those are the outputs. I did that backwards, okay? Input, measurement matrix, and output. No compression here. You have 12 inputs and you have 12 outputs. Now, I like to go off on different trigonometric functions, so I'll go off on a cosecant for a minute. To talk about the motivation for this. The first paper on this that I'm aware of came out in 1943, called by Dorfman, The Detection of Defective Members of Large Populations. That's really, really softened up from what it was. What was happening in 1943? World War II. So what was happening was the US was inviting many males to come and join the fight. And every single person who was invited to join was given a blood test to check for syphilis. Syphilis was pretty rampant in those days. I think they caught it originally from Al Capone and it went to everybody else. But syphilis was a big problem. So when the war started, every single soldier, take a blood sample, check it for syphilis, take your blood sample, check it for syphilis. This had 2 problems. Very slow. We don't want you here taking blood tests. We want you over there killing some Germans. And very expensive, too. So this guy Dorfman, he was a statistician. He looked at applying some binomial statistics to this. And based on all the information that he had from the 2 years of measuring 1 by 1, he was able to determine an optimum sample size to do groups of tests altogether. So I don't know what the optimum size was. Let's say it's 100. So he takes 100 blood samples, pours them all together, and he knew with probability X that that would have syphilis or not. And so you could eliminate most of the people that way. And once in a while there would be somebody with syphilis in a sample, and then you'd have to go and test all of those 100 people individually. But it was a very efficient way to do this. Now the second one here comes from Bell Labs, and this relates to what I said earlier. The original telephone system was analog, so how did they do filtering? Op-amps, resistors, and zillions of these things. Op-amps, resistors, and capacitors. So they'd buy a trainload of capacitors and hope they all matched, trainload of resistors, hope they all matched, and so on. So he was trying to find ways to test all those resistors in a big pile and determine what was good and what wasn't from a minimum number of tests. But anyway, that's the motivation behind compressed sensing. So here's the basic idea. Instead of having this identity matrix like I just showed you, let's assume we just roll out a 12-bit random number. So what we have here is the 12 possible weights. We roll out this random number which says take ball, let's see, 12, 11, 10, 9, 8, 10, and 11. Take those three balls and weigh them together and you get some result. That result is heavy. Okay? So this is fun. You can do Bernoulli, Toeplitz, circulant, all kinds of interesting one-bit or random codes to do this. So then say, okay, I'll roll it again. And so I generate another 12-bit random number, which is shown here, and you can see that collection of balls is there. And that's light. So up, not done yet. Roll it one more time. Ah, we're done. Why are we done? Can anybody see? If you look at these three sets of data, what do you get out of that? It's two heavy sets, but what's common between the two heavy sets? Only 10. So with a little bit of intelligence after the sampling process, the reconstruction process, you can say, I know that it's ball 10 because of this thing that I just pointed out. So that's how compressed sensing works fundamentally. It's very efficient for certain types of signals. Now what are those types of signals? Those types of signals are sparse signals. What's sparse about this? You have 12 balls and only one's heavy. That's sparse. If you take a heartbeat signal, why is that sparse? Well, think about the shape. You get a heartbeat, and then hopefully a short period of time and another one, and so on. So in terms of time, your heartbeat is active only for a small percentage of the total time of, 60 per second or 60 per minute, one per second, okay? So that's sparse in the time domain. What about a sine wave? Is that sparse? Not in the analog, not in the normal time domain, but if you take it into the frequency domain, how many results are there? 1, 60 hertz. So that's another thing about compressed sensing. There's all different domains that you can do this compression in based on what types of signals you're working with. So it's a pretty cool approach. I think DeGong did some frequency stuff and some, so was there some time stuff in there too? I don't remember. Yep, both in what he was doing on testing analog to digital converters. Okay, so that's the basic idea. How much can you compress? Well, this shows sparsity versus compression in general. 50% sparsity, you can't, you can compress by 2.5 or something like that. If you talk about 8-bit electrocardiogram or heartbeat signals, you can compress by about 6 or 7x. Wow. Pizza Hut. Okay. All right, so that's how much you can do. Now, you look in some papers, you always see lots of lies. I won't talk about any of those, but one's a Northeastern school in Boston who claims that they can compress ECG by a factor of 50. Being in Iowa, I would say bullpucky to that. That's it's theoretically, if you get about 6, that's as good as you can do with these kinds of approaches. Okay, this was done, a lot of this work was done within the last 6 or 7 years. A guy named Emmanuel Candes at Stanford did a lot of this stuff. Let's see, who were the other ones? David, what's his name at Stanford? You're not helping me, Dagong. A couple other guys, one at Stanford and one at UCLA. I can't remember their names right now. But this is pretty cool stuff, and it's pretty much brand new. So a lot of opportunities there. Okay, so you can do a couple of things here. You can use a Gaussian distribution for your random numbers, and that's kind of what these colors indicate, maybe a 6-bit code with different codes for the random numbers. Now, here's what, remember what I said is you take a signal in and so here's a representative of a heartbeat signal. We're compressing it by a factor of 4 here from 1,024 digital points down to 256. So here's what the compressed signal looks like in time. Now, the first time we saw one of those, momentarily at least, we thought, oh my God, what is that? It looks like junk. I had to search for the right word there. It looked like junk. But then we realized it makes sense. Why does that waveform look like that? Why does that make sense? What does it look like? What does that look like? In one word that starts with an N, what does that look like? Noise. Why does it look like noise? What is noise? It's a random thing, right? So what we're doing here is we're taking a signal and multiplying it by a random number. So, duh, it looks like random noise. So once we realized that, we didn't feel so bad, but it's a good observation to make. So a little bit about how the system works here. So we know now how to take our signal, bring it in, and compress it. So once you compress it, you transmit the digital information back to the hospital, to the doctor. There's an antenna, picks it up, and reconverts it back to digital. Now, this is a very asymmetric process. The part of gaining the data, compressing the data, very efficient, very easy. The reconstruction process can be very complicated because you can put this so-called baseband DSP there. Now, one of the things that, one way you can think about compressed sensing is it's a feature extraction technique. So if you take a heartbeat signal, for example, and you look at its shape, it kind of dips down, and then it goes up, and then it dips down again, and it looks something like that, if you can follow that. So I'm a lousy mathematician. I was talking to my students about this one day, and I said, hey, that kind of looks like a Mexican hat. And it turns out there is a wavelet called Mexican hat that you can use in the DSP box here to try to sort out that specific feature. So depending on what you're doing, you might choose different wavelets to look for different shapes and so on. But generally, that's a pretty complicated part of it. So if you do that in the doctor's office where there's plenty of power, you can plug into the wall and so forth, that's good. You put the rest of the stuff here, which is very efficient, that's good also. Okay, so those are some reconstructed signals. Nothing particularly, just got to show that it works well. So here's how we tried to implement this in Switched-Capacitor. This is not a very good block diagram, but I'll try to explain it. So you got your LNA out here that amplifies the signal. And then coming into each channel, there's M channels here. Remember, M is the number of possible compressed values that you get out. So you have a random number here, and you multiply the signal by that random number, and then you integrate it and convert it and send it off on the radio. So that all sounds really good. If you look at this in terms of switch capacitors, it really implements quite easily. So what we've got here is a switch capacitor DAC. So it provides an output whose amplitude depends on the digital signal that you put in here to switch the plates of the capacitors. So you put in a random number here, and you can create a random amount of charge that flows onto this output capacitor and gets integrated and so on. So that's basically it. So we have an LNA, which is off chip in this case. We've got these compression units for each channel and an A to D converter for each channel, and then into the power amplifier and off into the air. Switch capacitor blocks, we actually used C2C implementations rather than the binary weighted implementations that I showed here. Why would we use a C2C rather than a binary implementation? One of the students?
It's like Allstot and others for that, right? The same reason?
Slightly different. If you have to charge the capacitor array up to the value of the input signal, what's the total capacitance that you see in one of these structures, looking in from the bottom? It's like C or 2C. That's Shakespeare is famous for that, C or 2C. But in the previous case, you have all of these, you have 2 to the n capacitors here. So if you have 2 to the n versus 2, you save 2 to the n minus 1 power in charging up that much smaller capacitance. So for power reasons, we implemented these using C2C structures in the MDAC and C2C structures in the A to D. And these are the amplifier circuits. Okay, these are some more measurements done with the chip. I won't spend time on that. More measurements done with the chip. And finally, this is what the chip looks like. So if you look across this thing, there are 64 channels here. So 64 MDACs. So those are the capacitor arrays for the 64 MDACs. The 64 op amps are here. The 64 10-bit A to D converters are here. And we mux this stuff out to the power amplifier. Now, depending on what your compression factor is, you may use all of these, or you may only use 1 or 2 if you have a lot of compression. So the nice thing about this is it's pretty simple structure, and it's extremely power efficient. So for the ECG application, we only use 28 nanowatts per row. So even if the whole chip is active, it's only about 1.5 microwatts. It's a very low power solution. Okay, what else can I say about this? Chip size is probably reasonable. The number turned on depends on the compression factor that you're trying to achieve, and so on. Okay, so that's the chip, and that's the end. So I need to thank some collaborators. I always thank them because they work in industry now, and I'm hoping they'll give me some money. So here's some people at Intel and a couple of professors and so on, and some other students that worked on this, including my daughter, which was part of an undergraduate team here. So with that, I hope I've gotten you excited about switch capacitors. They're fun, and they're back, and they're doing everything. Medical, mixed signal processing, and RF. What else is there?
Power electronics.
There is even switch capacitor power electronics. Okay, thank you.